Alright, last example to wrap things up here. So we're supposed to compute the vector surface integral given this vector field, and then it says the surface is such. If you end up sketching this out, it might help you. If maybe not, I don't know. And if we end up sketching this out, what we end up with is a basic paraboloid. Okay, so here's our paraboloid. Here we go. Something like this. Okay, and it says with a downward pointing normal vector. So if we're looking on the surface, it should be pointing like this, okay, and like that, okay. And so what I'm going to do is I'm going to make use of Stokes' theorem, most certainly, but I'm going to make in use of the corollary in particular. So I could compute the boundary of this and do a vector line integral over that. That can be fine. Gets a little messy, let me tell you. So I'm not going to do that. And similarly, if I compute the the vector surface integral, that gets to be a little messy as well. But what I notice is that there's this nice boundary here, right? And this boundary would not be included, right, normally? So what if I instead do Stokes' theorem over that by the corollary, right? They're parameterized by, they share that same boundary, all that good stuff. I believe all the assumptions of the corollary are met. So if I look at this and I look at parameterizing this, this should be a parameterization y of r and theta, where in particular we have r cosine theta, r sine theta, and 1 being our parameterization for that surface. And then I can compute the, I can do a vector surface integral with this, and by Stokes' theorem and that corollary, they're going to be the same. Alright, so with this, let's go ahead and just kind of buzz through computing the vector surface integral. So we have to find TR, which ends up being cosine theta, sine theta, cosine theta, sine theta, and 0, and then T theta is going to be negative r sine theta, r cosine theta, and 0. Okay, and then when I cross TR and T theta, okay, this is going to give 0, 0, r. Okay, but keep in mind that this is pointing upward, right? And we want downward, so that means that the downward is 0, 0 minus r for downward. Okay, so then I can also compute the gradient cross f, okay, and I did this off on a different sheet of paper, and because the vector field is oh so fun, what we end up getting is 2, negative 5, and negative 2. Okay, so that's grand. So then if I go ahead and then compute, let's call this S2. Let's do this double integral over S2. Well, okay, double integral over S of this, and then, cross, dotted with ds. This is going to be the same as double integral over S2 of gradient cross f, dotted with ds. Okay, and so this is going to be now 0 to 2 pi, 0 to 1. Okay, and then we have the normal vector here, so 2, negative 5, negative 2, okay, dotted with 0, 0 minus r, and then dr d theta. Okay, and long story short, we end up getting 2 pi. Okay, so punchline here is remember to make use of that corollary. So if you have a surface integral that looks to be, or the vector surface integral that looks to be a little bit messy, again, look for that complementary region or something that shares the same boundary, and then you can say that the vector surface integrals are going to be the same using Stokes' theorem, again assuming all those conditions apply. I didn't go through and verify conditions, but you always should. And then we can move on with our lives. Alright, so we'll see you in class later.